Good day, everyone. This is the beginning of Module 5. And in order to understand this module, we need to know what a MOSFET is in the first place. If you have not heard of a MOSFET, it is a type of transistor which we are familiar with from Module 5, Module 4 that is. It is a type of transistor, and just like BJT, it has three terminals. The symbol for a MOSFET looks like this. Just like BJT, it can be NPN or PNP, but we call it in a different way. That is, instead of NPN, that is, we call it a P channel and N channel MOSFET. Okay, this is an N channel MOSFET, or otherwise called NMOS in short. This is a P channel MOSFET, which is in short referred to as PMOS. Okay. N-channel MOSFET and P-channel MOSFET, both of them have 3 plus 1, actually 4 terminals, but only 3 terminals are indicated here because the fourth terminal is shorted and grounded. The 3 terminals are source, gate and drain. For PMOS also, there are 3 terminals: source, gate and drain. Okay. Current always flows from source to drain, from source to drain. Okay. The physical structure of a MOSFET looks like this. We have source, gate and drain. So if I take a cross section of the MOSFET, this is a cross section of the MOSFET, it would look something like this. I have, this is any type of semiconductor. Let it be a P-type semiconductor. So we call it P substrate. The base semiconductor is referred to as substrate. So this is a P-type substrate or P-type semiconductor. Okay. Inside this P-type semiconductor, we have made a portion of N-type region. Like I said, this is a cross section. So the 3D image would look something like this. We have N-type region. This much region is N. Okay. As you can imagine, under this also, it is N region. Okay. I hope that makes sense. And then you have, this is one terminal. From this you can take contact, metal contact. This would be your source. Your drain will be at the other end and it will look exactly like your source. It looks exactly like your source. This is your drain terminal. Okay. This is your drain terminal. Now, you would wonder, if they look exactly same, what makes this terminal source and what makes the other terminal drain? Strictly speaking, they are physically identical and therefore source and drain can be interchangeably used or connected. But once you connect it in the circuit, you will intend one terminal as the source and the other terminal as the drain. And thereby we will be doing the design. So once you have fixed the source in the circuit, you will not change it. At the same time, you can pick any one of these two terminals as the source and the other as a drain, so to speak. Okay. Still, one of them is designated as source and the other is designated as drain. In between the source and drain, you have what is called the gate region. In this gate region, on top of the semiconductor, we will be layering it, or a layer of silicon dioxide is grown. A layer of silicon dioxide is grown. Okay. There. Layer of silicon dioxide is grown. As you can see, it is above the semiconductor. Okay. So this is your layer of silicon dioxide. Okay. And on top of this silicon dioxide, from there you will take the contact of the gate. So from here you will be taking the contact for the gate. So on top of the semiconductor, or sorry, on top of this gate, you will have a layer of metal in order to take contact. Okay. Like we said, this is your drain. For clarity, I'm just moving the contact of drain over here. I hope that's okay. Okay. Now we have three terminals, that is the source, gate and drain. And this is what the physical structure of a MOSFET looks like. This middle region is your gate region. On one side you have the source and on the other side you have the drain. Okay. N region, in between you have P region, and on the other side you have again N region. Okay. Next question is, how does this MOSFET work? What is the basic working of this MOSFET? In order to understand the working, I'm going to simplify this diagram and only draw the front face of this cross section. Just draw the front face of this cross section. What would that look like? I have the MOSFET, source, drain, okay, source, drain, and in the middle you have silicon dioxide layer, and on top of it you have metal layer. See, this is metal, this is silicon dioxide, and this is semiconductor. Therefore, the mystery of how the name came is solved, isn't it? MOS, metal oxide semiconductor at the gate. Okay. Field effect transistor is the name of a category of transistors that are voltage controlled. Okay. BJTs were transistors that were current controlled. The other class of transistors is FETs, field effect transistors. Field stands for electric field. Electric field is present when there is a voltage. Therefore, field effect transistors are transistors that are controlled by voltage. You got the idea. And you understand what MOS stands for now. Now, if I take N, P, N, like I said, this is not referred to as an NPN MOSFET. This, in fact, is referred to as a N-channel MOSFET. You will understand why it is called an N-channel immediately right now. Okay. This is your source and this is your drain. In order for this MOSFET to conduct current between source and drain, a current should flow. So for current to flow between source and drain, okay, between source and drain, there should be a potential difference, of course, but you notice that even if there is a potential difference, there is a P region between two N regions, which means there is no connection between this N, source N and drain N. We need to form a connection or a bridge between these two. If there was a bridge like this of N-type material, then current could flow between these two regions easily if there is a potential difference. Okay. Let me say that again. In order for current to flow between source and drain, there is no path. Okay. To create that path, I need a region of N between the two ends. It's like a bridge. And it's actually referred to as a channel. I need that kind of a channel. Now, to create this channel, I have to bring in electrons. Electrons make the material N-type, isn't it? Because as of now, when we have not applied any voltage anywhere, this is purely P-type. I have to convert this region right below the gate into from P to N. How do I do that? It is already P-type, meaning there are lots of holes here. I have to convert it into a region containing electrons. How do I do that? In the first place, I have to get rid of these holes. To get rid of these holes, I have to remove these holes. Remove as in I can use recombination method. If I have some mechanism of bringing in some electrons and making it recombine with the hole, then we could slowly get rid of these holes. And what will we end up with? We will end up with a depleted region. This depleted region, again if you bring in electrons into the depleted region, now the region will be dominated by free carrier electrons because no more recombination can take place, but it is filled with electrons. Let me say that again. In order to create a region, a channel of N-type, what should I do? First of all, this region is dominated by holes. I have to get rid of the holes. So by some mechanism, if I can bring in electrons, make it recombine with the holes, one by one, I can get rid of these free carrier holes. If I get rid of the free carrier holes, these become a depleted region. In the depleted region, there is no free carrier, neither holes nor electrons. Now, all I have to do is continue bringing in electrons so that they will fill the depleted region. Ultimately, there will be a region filled with electrons, which is what we call N-type region. Now, we have got our required N-type channel. Yes. Now, next point is how to make this happen. In order to make this happen, we apply a positive voltage at the gate. We apply a positive voltage at the gate. The positive voltage will attract any, even if it is minority carriers, there are electrons in the p-type region. Okay. These electrons are attracted to the gate region because you have applied a positive voltage here, a huge positive voltage. These minority carriers are attracted to the channel area. These electrons will combine with the holes that are dominating this channel area. Thereby, over time, if your gate voltage is strong enough, all the holes will undergo recombination and there will be a depleted region formed here. Okay, this is a depleted region. Into these depleted regions, I further increase the gate voltage such that the positive voltages increase such that the minority carriers of electrons keep coming into this gate region. As the minority carriers fill the gate region, ultimately I have a region that is dominated by electrons, which is exactly the definition of an N-type region. Now I have an N-type region. At a particular gate voltage, the channel is just formed, and that particular gate voltage is referred to as threshold voltage, VTH. Threshold voltage is a voltage at which the channel in a MOSFET is just formed. Okay, and this region, it was P, now it has been converted into N type. That is, the channel has become inverted. It was P, it became N. Therefore, it is inverted, became the opposite. Therefore, this is also referred to as inversion region. This is also referred to as inversion region or inversion layer. Okay. Yeah. Now at this threshold voltage, gate channel is formed. Now, like I said, there is actually one more terminal, and that is the body of this MOSFET. The body of the MOSFET is taken from this substrate that is here. Okay. And usually it is connected to ground. Usually the source is also connected to ground. The source is also connected to ground. Therefore, the bulk and source are usually shorted. That is why we do not show this in the symbol. We do not show the bulk in the symbol because it is usually shorted with the source. You get the idea. Now, the only thing that you need in order for current to flow is a potential difference between gate, source and drain. If source is ground, let me apply a positive potential at the drain. What happens? The positive will attract the electrons from the channel and therefore electrons will flow out of the drain. Okay. That is, electrons flow from source to drain inside the semiconductor. Electrons flow from source to drain inside the semiconductor, as you can see. There are electrons here in the source region, electrons in the N region, and there are electrons between them. Therefore, naturally, if there is a potential difference, the electrons will easily flow from source to drain inside the semiconductor and out of the drain outside the semiconductor. Okay, this is how current flows from the MOSFET. Okay, so this is the basic working of a MOSFET.